robins that are all flying in roughly the same direction, some of which will have made the journey many times before. Her night vision is superb, but she is not looking for any landmarks, as we might were we making such a journey. Nor is she tracking the pattern of the stars in the clear night sky by consulting her internal celestial map, as many other nocturnal migrating birds do. Instead, she has a rather remarkable skill and several million years of evolution to thank for her capacity to make what will become an annual autumn migration, a trip of some 2,000 miles. Migration is, of course, commonplace in the animal kingdom. Every winter, for instance, salmon spawn in the rivers and lakes of northern Europe, leaving young fry that, after hatching, follow the course of their river out to sea and into the North Atlantic, where they grow and mature. 3 years later, these young salmon return to breed in the same rivers and lakes where they spawned. New World monarch butterflies migrate thousands of miles southward across the entire United States in the autumn. They, or their descendants, as they will breed en route, then return north to the same trees in which they pupated in the spring. Green turtles that hatch on the shores of Ascension Island in the South Atlantic swim across thousands of miles of ocean before returning, every 3 years, to breed on the exact same eggshell-littered beach from which they emerged. The list goes on. Many species of birds, whales, caribou, spiny lobsters, frogs, salamanders, and even bees are all capable of undertaking journeys that would challenge the greatest human explorers. How animals manage to find their way around the globe has been a mystery for centuries. We now know that they employ a variety of methods. Some use solar navigation during the day and celestial navigation at night. Some memorize landmarks. Others can even smell their way around the planet. But the most mysterious navigational sense of all is the one possessed by the European robin, the ability to detect the direction and strength of the Earth's magnetic field, known as magnetoreception. And while we now know of a number of other creatures that possess this ability, it is the way the European robin, Erithacus rubecula, finds her way across the globe that is of greatest interest to our story. The mechanism that enables our robin to know how far to fly and in which direction is encoded in the DNA she inherited from her parents. This ability is a sophisticated and unusual one, a sixth sense that she uses to plot her course. For like many other birds, and indeed insects and marine creatures, she has the ability to sense the Earth's weak magnetic field and to draw directional information from it by way of an inbuilt navigational sense, which in her case requires a novel type of chemical compass. Magnetoreception is an enigma. The problem is that the Earth's magnetic field is very weak, between 30 and 70 microtesla at the surface, sufficient to deflect a finely balanced and almost frictionless compass needle, but only about 100th the force of a typical fridge magnet. This presents a puzzle. For the Earth's magnetic field to be detected by an animal, it must somehow influence a chemical reaction somewhere in the animal's body. This is, after all, how all living creatures, ourselves included, sense any external signal. But the amount of energy supplied by the interaction of the Earth's magnetic field with the molecules within living cells is less than 1/1000th of the energy needed to break or make a chemical bond. How, then, can that magnetic field be perceptible to the robin? Mysteries, however small, are fascinating because there's always the possibility that their solution may lead to a fundamental shift in our understanding of the world. Copernicus's ponderings in the 16th century on a relatively minor problem concerning the geometry of the Ptolemaic geocentric model of the solar system, for instance, led him to shift the center of gravity of the entire universe away from humankind. Darwin's obsession with the geographical distribution of animal species and the mystery of why isolated island species of finches and mockingbirds tend to be so specialized led him to propose his theory of evolution. And German physicist Max Planck's solution to the mystery of black-body radiation concerning the way warm objects emit heat led him to suggest that energy came in discrete lumps called quanta, leading to the birth of quantum theory in the year 1900. So could the solution to the mystery of how birds find their way around the globe lead to a revolution in biology? The answer